All right, so chugging right along to chapter 17. So I've said this semester is about electromagnetism. We've talked a lot about the electric side of that, but now we're going to bring in magnetism, and we're going to build to see how they're beautifully related. So electric fields are not the only fields associated with charged particles. So you also have magnetic fields, which are made by moving charges. And you've already seen examples of this. And you have already seen this in lab. So we've seen it, now let's work on understanding it. Okay, so when you've got a wire with a current running through it, what you have is an electron current. And what this is all going to build towards is really understanding circuitry. So circuitry equations are important for a variety of different applications, but what we're going to do in our approach is we're going to understand the physics behind where they come from, and the extent of their limitations, which can be useful for a lot of different building intellectual paths. So circuits come about by arranging conditions so electrons are constantly moving. All right, so the definition of an electron current, and please note that I am intentional in using the word electron in front of this because we're going to clarify two different types of currents. So the electron current I, so it's denoted by a little I, is the number of electrons per second that enter a section of conductor. And by the way, you can actually think there's some overlaps between thinking about currents, electric currents and fluid currents. I will bring in some fluid mechanics later on into this course. And so you'll be able to actually see the similarities between the two. And there are two impacts of having an electron current through a wire. So you have the heating of the wire, which is proportional to, and you have the induced magnetic field. Both of these can tell you something about the electron current going through that wire. Okay, so let's talk about how we detect these magnetic fields. And again, you've already done this in lab, so this is going to be a nice review. So typically, we can use a compass to detect magnetic fields. I mean, we've been using compasses for millennia. All right, so, but you might ask, how do we know a compass is not responding to electric fields? Well, if you were in class, you would see me wave a charged rod over a compass and see it does not respond at all to it. So next time you are in lab, you should try that for yourself. But you will see a compass respond when you have a current carrying wire. So, by the way, this response was discovered entirely by accident. Orsted was teaching class, talking about electric currents, happened to have a compass on the table because I come from a long tradition of physicists that have messy workspaces, and he saw that the needle deflected when current was running through the wire. So, when you see these effects, you can see by examining the compass that B depends on the electron current. If there's no current, then there's no magnetic field, and the magnetic field is perpendicular to current direction. All right, and also the direction, of B under the wire is opposite to the direction of B above the wire. So let's draw the fields. So we know the Earth has a magnetic field. So we need to, and that is also impacting the compass. So if you align your wire due north, you'll have the field from the Earth, and then you'll have the field from the wire, which is perpendicular, and then this is your B net, which is the combination of both the field from the wire and the field from the Earth. And so, if you have a wire with huge current running through it, then it's going to be much, much bigger than the field of the Earth, and you would get 90% deflection. Obviously, we're not going to do any experiments like that with that large of a current because there's some safety considerations. So let's look at an example on how to calculate the field of a wire. A current carrying wire is oriented north, south, and put on top of a compass. The magnetic field of the Earth is 2 times 10 to the minus 5 Tesla. And the magnetic field of this wire is 2.6 times 10 to the minus 6 Tesla. What deflection is observed? This is sort of the opposite of what you did in lab. So theta equals arctan of B wire over B Earth, which is equal to arctan 2.6 times 10 to the minus 6 Tesla over 2 times 10 to the minus 5 Tesla, which is 7.4 degrees east. All right.